Okay, continuing with chapter 4 and section 7.4. Now we come to doing the stoichiometry. Stoichiometry is defining this term called the mole, all right, and then being able to convert grams of reactants to grams of product and so on, all right, okay. But first we need to define this quantity called the mole, all right. So what is the mole? As in this picture you can see, if you have a dozen eggs, that word dozen is the numeric value is 12. So it doesn't have to be eggs. It could be a dozen rabbits, a dozen pencils, but the value associated with that term dozen is 12. Or it could be a ream of paper, which means 500 sheets of paper. One gross, which I've never encountered before, not commonly encountered, is the numeric value is 144. One case, 24 cans, like in the case of soda, all right. So there are these terms, these defined terms, and there are certain values associated with that term. The mole is one such quantity in chemistry, which helps to simplify things, all right. And the number associated with mole is 6.02 times 10 power 23. This is also referred to as the Avogadro number. And if you write out all those zeros, as you can see, that's a lot of zeros, all right, a really big number. So this number was defined, and the reason this was defined is because a mole, these many items of, say, atoms, or these many items of molecules, becomes visible, all right. A single atom or a single molecule is completely invisible, hard to work with atoms and molecules because we can't see them, all right. But if we were to work with these many numbers of atoms or molecules, it's easy to see them, all right. What I mean by that is, if I have 6.02 times 10 power 23 atoms of aluminum, for example, that's a mole of aluminum, and it should weigh around 27 grams. 27 grams is something tangible. I can weigh it out in the lab on my balance. Whereas one single atom of aluminum, I won't be able to do that, all right. So this number is able to convert really tiny particles into something tangible that we can work with, especially when we are weighing out substances, all right. Our 6.02 times 10 power 23 molecules of H2O, that means that's 18 grams of H2O, all right. Again, 18 grams, it's visible, all right. One single molecule of H2O, it's hard to visualize, okay. So a mole of an element, that means there's 6.02 times 10 power 23 atoms of the element. Like, for example, the aluminum example, or if it is hydrogen, all right, a mole of H2 gas would weigh around 2 grams, all right. H2 is 2 atoms of hydrogen, so that would weigh around 2 grams, all right. A mole of carbon would weigh about 12 grams. That's 6.02 times 10 power 23 atoms of carbon. Or a mole of sodium, 6.02 times 10 power 23 atoms of sodium would weigh around 23 grams, okay. Or a mole of sulfur, like here, 6.02 times 10 power 23 sulfur atoms, that's 32 grams, okay. So if it is a mole of an element, that means atoms of that element. If it is a mole of a compound, it means molecules of that compound. If it is a mole of an ionic compound, then instead of molecules, we use the word formula units, all right? Because technically NaCl is not a molecule. They are charged particles, and those charged particles are called as formula units. All right, so mole can be used as a conversion factor, right? 1 mole over 6.02 times 10 power 23 and vice versa. All right, so when you are converting atoms to moles or vice versa, again, use the appropriate conversion factor. State what is given to you, what you need to do to get from point A to point B. Write out your plan. Use that conversion factor, the Avogadro's number, set up the problem, and calculate for the unknown. So here you're asked to find out how many carbon dioxide molecules are in a half a mole of carbon dioxide, right? So 1 mole of carbon dioxide is 6.02 times 10 power 23. So half a mole would be half that amount. Okay. So 1 mole is 6.02 times 10 power 23. Half this amount would be 3.01 times 10 power 23. Okay. The number of atoms in 2 moles of aluminum, right? So 1 mole is 6.02 times 10 power 23, all right? 6.02. 2 times 6, that will be 12. So 1.2 times 10 power 24, all right? 12.10 power 23, or if you move the decimal point between the 1 and the 2, 1.2 times 10 power 24. The number of moles of sulfur in 1.8 times 10 power 24. All right, you're going from such a large number, then your your final number is going to be a small number because you're going to divide this by 6.02 times 10 power 23. All right, and so when you do that, it should come out to be 3 moles of the sulfur atom. Okay, so you divide the 6 by this, so it's almost like dividing 18 by 6, and you get 3 moles of sulfur atoms. All right, so when you have a formula, how do you interpret the formula? If you had one single molecule of this aspirin, you have 9 atoms of carbon, one single molecule, 8 atoms of hydrogen, and 4 atoms of oxygen. However, if you have 1 mole, that means 6.02 times 10 power 23 molecules of the aspirin, then the interpretation is 9 moles of that is carbon, 8 moles of that is hydrogen, and 4 moles of that is oxygen. So it depends on what you're looking at. Are you looking at one molecule, or are you looking at a mole of the compound? All right. If you're looking at a mole of the compound, then instead of atoms, you're talking in terms of moles of the elements. So the subscripts are telling you how much of each atom or each element is present in this compound. And then you can write conversion factors for each of that, all right? Okay. 1 mole over 9 moles of C and so on, all right? So for each of the elements you can write. So you get a possible of 6 conversion factors, okay? 2 for each element. All right. So when you're calculating moles of an element in a compound, again, look at what's given to you. What do you need to calculate? Write out the plan. Write up conversion factors and equalities using the subscripts, and then set up the problem and convert for the unknown. So how many atoms of O are in 0.15 mole of aspirin? Okay. So if you look at the aspirin formula, For 1 mole of aspirin, you have 4 moles of O. All right. So if you have 1.5 moles of aspirin, how much would it be? Okay. So that would be around approximately 6 moles of O, right? Okay. 1 is 4 moles, and then add on another half mole, and so you should get around 6 moles. Okay. And then it says further, all right, how many atoms are in this, how many atoms will that be equivalent to? All right, so first convert the mole of aspirin, the 0.15, oh, this is incorrect. It should be 0.15. So convert the 0.15 mole of aspirin into moles of O, all right, because for every mole of aspirin you have 4 moles of O. And then 1 mole of O is 6.02 times 10 power 23 atoms. All right, so that final answer, 3-sig fix, will come out to be 3.61 times 10 power 23 atoms of O. And we will stop here.